All right, well, welcome to another lovely day of vector calculus. Not so lovely the weather up here in the Tahoe, Carson region. Um, but hey, winter had to hit us eventually, so I guess we're starting to get it. Today's plan, I want to do a little bit more with surface integrals, right? Because I kind of introduced them to you, but I want to show you one of the big things we do with them, which is the flux integral. So I want to show you that. And then I also want to then spend the rest of the time preparing us for the exam that's going to be on Friday. So we'll go over the quiz and the quiz you guys just took. I have not finished grading them yet, so that will happen by tomorrow. But at least this way you can see the steps and everything for those problems. And then after that, we'll review for the rest of the remaining time on whatever you guys would like. So that's my plan. But before I take over and start driving, as always, are there any questions about any of the homework sets or anything that we've talked about that's unclear that you'd like to touch up on or look at? All right, well, hearing none and seeing none, I'm going to go ahead and switch to the whiteboard and I'll be back with you in just 1 second. All right, so last time we were looking at surface integrals. So let me just remind you what those are. They're basically the same idea as a line integral, except instead of integrating just over a curve, we're integrating over an entire surface, right? So we're now integrating over a surface. I forget which, I think we used the letter S for our surface. So S is just some old surface. We're going to be integrating our function. I'm going to go ahead and call it f of x, y, z. And then we've got a dA. So this dA, this is surface area, right? We're integrating over the entirety of the surface area. All right, so this is the idea, super simple idea. But to put it into practice, we want to parameterize just like we did curves. So the surface, if we define it as a function of u and v, where u and v are our two parameters, then this changes a little bit. So we're integrating over this guy s. The function, we're going to substitute in the u's and the v's. And then we saw that this remaining piece, we had to have a Jacobian. And in this case, the Jacobian is the magnitude of RU cross RV, where RU and RV are the partial derivatives with respect to U and V of this parametric surface. And then we get our du dv. So this is the setup that we want to use. And it's just a matter of blitzing through and doing that integral. All right, when this function is equal to 1, then the result is the surface area. And that's pretty much the one and only application we've talked about or done, but I've hinted at some other things that you can do with it. Like, for example, if you wanted to find the mass of a surface, if you knew its density, integrate the density over it. If you wanted to know the total charge on a surface, if you knew the charge density, you could integrate that over the surface, or this, that, or the other thing. Okay, just whatever it is we want to add up over surface, that's our function. but really we end up doing this parametrically. And when it comes to parameterizing surfaces, we spent quite a bit of time last time looking at how to do that for specific types of functions and or surfaces. Remember your conversions for things like spherical and cylindrical, because those can be useful. I also showed you for surfaces of revolution. And we also talked about functions of xy, surfaces that are functions of xy. Those are the easiest. You let x equal u, y equal v, and then z equals whatever that function is. Okay, so just a little bit of a review of where we were. So what we're going to do today, we're going to go a little bit further. Before we do that, though, we need to talk about orientation. So just like curves, we need to talk about basically direction for surfaces, right? Because like when we did line integrals, think back to when we did line integrals. Just a regular old line integral, the direction on the curve didn't matter, right? Like we just had to parameterize the curve and then integrate, and we could get like the mass of it or something, right? Like think about a wire. It doesn't matter which direction we go to add up the masses on the wire. We're going to get the total mass once we're done. But when we went to other kinds of line integrals, like work integrals, flux integrals, that kind of thing, orientation definitely mattered. The work done on a path, if we go the opposite direction, wasn't the same, but usually isn't the same, right? If the work is 0 going one direction, it's going to be 0 going the other way as well. But in general, we saw that we got a different value if we went in a different direction. And for us curves, it makes total sense, orientation. You just point an arrow in the direction that you're going. Well, we need to do the same thing for surfaces. If a surface is orientable, surface actually has sides to it, we need to be able to describe the surface integral relative to which side we're doing. Okay, so, and that's what surface orientation is. So think about this. Just think about this. I give you a surface, and I say, find me a unit normal vector. Is that, like, is there going to be a unique answer to that? So Victor says yes. What do the rest of you guys think?
I think so too.
All right. So Bradley's got your back, Victor. Good to know. All right. So does Jacob. All right. So you guys are all like, yep. So there's, like, when we did it, there was a big N, right? There was a unit normal vector to a curve. And now if we go to the surface, you may go, okay, yeah, there's one. Well, it turns out, no, it's not unique. Even if we specify unit, so length 1, I'm not worried about all the different possible lengths, but given a surface, there's more than one. Let me get a surface real quick. Okay, here's a surface. I wanted to grab this and not a book or something because I can bend it. But let's just say it's a plane. Okay, so here's a surface, here's a plane. And I want a normal vector. And let's make this a unit. So this is length 1. Well, here's one. There's a unit normal vector. But there's also one on the other side. We ran into this problem with curves too. You may remember when we talked about normal vectors, the principal unit normal vector was the one that always pointed to the inside of the curve. Well, excuse me, we have to worry about that too, because now if I bend it, all right, so let's say it's, here you go. So now my surface is a cylinder. Yeah, I can't put my pen on the inside. So a portion of the cylinder that's bigger, right? So curved. There's a unit normal vector. There's a unit normal vector. There's always two when you've got an orientable surface. Okay, so we're going to have to specify which direction we're going. What direction is our orientation? I know this feels weird. I know this feels wrong, but we have to do it. We have to be able to describe which direction the surface is, or that we're integrating over the surface. Don't think of it as direction. That's totally the wrong way to think about it, but it's the equivalent of direction for line integrals. Okay, so first things first, not all surfaces are orientable. Not all surfaces have two sides to them. And I know that that also feels weird, but it's truth. There are curves, there are surfaces that don't have two sides. Now, most of the surfaces you think of do. A sphere definitely does. There's the outside, there's the inside. Think of it like an elliptic paraboloid, a bowl, right? Bowls have kind of the top part and the under part. In fact, every function of x and y is orientable, right? You can either be pointing upward with a normal vector or downward. But it is possible for a surface not to be orientable. Probably the most famous one is a Mobius strip. So do you guys know of the Mobius strip? Have you heard of the Mobius strip?
No.
No? Okay, I'm going to make one.
It's a surface with just one surface, right? Like,
Yeah, it's a
that doesn't
surface.
make a lot of sense.
A surface with only one surface? Yeah. It's a surface with only one side. So I'm going to make one. I'm going to just tore off a little strip of paper. Now this clearly has two sides to it. You can see that this side is white, plain. That one's got some writing on it. I don't know if you can see, but it's got some marks. So there's definitely two sides to this. This is an orientable surface. I've got side one and I've got side two. Now, if I were to connect these just like this and make a ring, okay, so like I'm making a little paper chain or something like that, this is still orientable. It still has two sides. It's got the outside, which is the clear side, and it's got the inside. I don't know if you can see, but you can see the marking on it, right? So it's still got the inside and the outside. So this is equivalent to that, right? It's still orientable. But here's how I'm going to make it so that it's not orientable. When I go and I connect these, I'm going to give it a twist first. Okay, so I'm actually going to twist. So instead of connecting straight up like that, I'm going to give it a twist. Okay, so now you can see that it's connected, but there's a little bit of a twist, like I'm tying a knot. Now I didn't actually tie a knot. I am just connecting the ends, but there's a little bit of a twist. Okay, give me 1 second here. Needed to find something to connect it here. So let me just staple it really quickly. It's going to free up my hand from having to hold it. Okay, now I'm going to prove to you that this only has one side. And I know what you're thinking, wait a minute, it can't have just one side. It had two sides before you just connected it. It still has two sides. Well, here's what I'm going to do. I'm going to take this pen and I'm just going to start drawing on the surface. And all I'm going to do is I'm just going to keep rotating the surface so that all I'm doing is just writing where it is. Okay. Now, if this has two surfaces, that means that when I'm done, there's going to be part of this that's not written on. Right? However, you know what's coming because I never do this sort of thing unless I know it's going to work. It's like, don't ever bet with me on non-sports stuff, because sports stuff I can lose because I don't know the outcome. But don't make me bet. If I bet you on something else, never take that bet because I only bet if I know I'm right. Okay, so check it out. So here we go. You're going to see I'm not doing anything funky. I'm just drawing. I am moving along with the paper, right? But I'm not like lifting my pen. nothing. Hopefully you guys can all see that. So I'm just going to keep drawing here. I'm almost done. Okay, so I stopped because I got back to where I started. But now let me show you that both sides of this paper have writing on the entire bit. So I'm just going to undo it again. Let's take off the staples. But here's this side, right? Pen, 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 right? You don't see any right here because that's where the thing was overlaid. But if I flip it over, again, that's where it was overlapped. But pen, 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 pen. So when this is twisted and put back together, there's only one side. Okay, so not all surfaces have two sides. It is possible to have weird things like this. Now, what happens with this one, like how you can tell that it's not orientable, is if you were to describe this parametrically and you looked for the normal vector, the normal vector doesn't change smoothly. There's a rapid jump in the normal vector as you move from one portion of it to another. It's kind of analogous to, remember when you had functions that were differentiable versus not differentiable? And that was like the tangent lines all moving nicely, and then all of a sudden there's a quick change to it. There was a sharp kink or something. Kind of similar idea with this. All right, well, we're going to restrict ourselves to orientable surfaces. We're not going to do Mobius strips. Trying to do a surface integral on a Mobius strip, it's a whole nother beast. So instead, we're going to look for orientable surfaces that have two distinct sides. An inside and an outside, a left and a right, an up and a down, however you want to think about it. Okay, so when they are orientable, this means that we can start doing things kind of like we did with line integrals. We can do a vector surface integral. Right, go back to line integrals. We did the whole just integrating a function, but then we went to a vector integral. That was the work integral, where we were integrating in a vector field. Well, we can do the same thing here with surface integrals. All right, so in terms of the orientation, basically this is how it plays out. You pick one of the sides to be positive. The other side is negative. Which one doesn't really matter. You can decide it however you want. There is kind of a standard though. There's kind of a standard. If you've got a field, and you can see where things are flowing. If the arrows of the field are pointing in the direction of one of the two, or, away from the surface, one of the two sides, that's the positive side. So think about this one. Suppose we had a field that was a three-dimensional field. That's vectors that are pointing away from the origin. Okay, so they're radiating out from the origin. So then if we had, say, a sphere, vectors pointing outside are going to be positive because those are pointing in the same direction as those field vectors. And the ones inside, we'd say that's the negative direction. So that's standard practice when we have a field and you can clearly see which direction the field lines are pointing. If you don't have that, just pick your favorite to be positive. Now, the other thing that we do that's pretty standard with surface orientation is if our surface is z equals, right? Because we have lots of those, right? Functions, surfaces that are functions. We tend to use either upward, and the upward orientation, this is the one that we consider plus versus downward. And when I say up or down, it doesn't mean that the vectors are pointing straight up or straight down, just that their z component is either positive or negative, or upward or downward. So take, say, a elliptic paraboloid, right? So a bowl like this. The downward orientation would be the vectors that are on the outside of that bowl, because those all point downward in the z direction. Again, remember it's three-dimensional, so that there are some like coming out and pointing towards you, and there are also some going into the board. If we were on the interior of that cup, now those tangent vectors are pointing upward a bit. So that would be upward orientation. So that's kind of a pretty standard one to do when we've got a function. And you guys are probably not surprised that functions show up a lot. I mean, they tend to show up a lot anyway. So even with these, we'll have surfaces that are with upward or downward orientation. All right, so one of the big things we do with surface integrals, beyond just adding something up, is to do flux integrals. Now, these are flux integrals over a surface. Which is different than a flux integral over a curve, but it has the exact same idea. It's still a measure of flow through that surface. Like before, we were looking at flow through a curve. Now we're going to be looking at flow through a surface. So we're just extending ourselves up a dimension. All right, so how did we do flux integrals before when it was a curve?
F dotted with little n.
Okay, so we did f dotted with little n. Let's actually, that's the usable, but the like definition was f dotted with n, big N, right? Well, that's exactly the same thing that we're going to do here. We're going to integrate over our surface f dotted with n dA. So again, our little surface area. Because we're measuring the same thing, right? Like if you think about why did we do f dotted with n, is it was finding the piece of the field vector that pointed in the direction of n, pointed normal to the surface, or to the curve. Well, we want the same thing. It's just now this n has to be normal to the surface. And by dotting it with f, we're finding the portion of the field vector that is pointing orthogonal to the surface. So it's exactly the same idea. It's exactly the same setup. It's just, okay, well, that guy's in. It's just a double integral. All right, now, in terms of practical use, though, again, we want to go ahead and get our unit normal vector, change it into u's and v's, and do all that. Now, let's think about finding a normal vector to a surface. What do you have to do to find a normal vector to a surface? You guys remember from last quarter?
Find the gradient.
Okay,
right?
so we can use the gradient because we know the gradient is normal to the surface. It's normal to level curves, right? And then, okay, so we can find the gradient. Or, okay, thanks, Victor. In fact, I was going to pick on you because I know you've been studying this stuff. But we can find the tangent plane and the normal vector to the tangent plane is going to be normal to the surface. So I don't know if you remember doing it that way. And the easiest way to do that, to find two vectors that are in that plane, are the partial derivatives. Yeah, no, maybe so. Right?
Yeah.
So you can find the g sub x, or the f sub x, the f sub y, cross them. That gives you normal vector, and then you just have to divide by its magnitude. Okay, well, the reason I'm bringing that one up as opposed to the gradient, and Bradley, if I have a choice, I go gradient, totally, because gradient's easy. But this one I want to show you just because you'll see why. If we think about this n, to get n, we can take our surface and take its partials. This thing is now normal to the surface. But to make it an n, a big N, so just magnitude 1, we got to divide by its magnitude. Right? So that was n. Well, just think about it for a second. What was the dA? What showed up in the dA? Yeah, so Victor just put in the chat box the magnitude of that cross product. Remember that was the Jacobian for this transformation. Okay, well, if this is n, and then dA is the magnitude of RU cross RV du dV, when I multiply those together, check out what goes away. That magnitude is gone. So for the flux integral, the usable form of the flux integral is we're going to change our field, so it's in terms of our surface, our parametric form of our surface, and then we're going to dot that with RU cross RV. All right, so this is the practical form. This is what you're going to use when you do this. All right, so that's kind of nice. But let me show you what happens specifically when we look at a surface that's a function. Okay, because the surface that's a function, oh, it's really nice. All right, so if we've got a function, z equals f of xy, the easiest parameterization is to call x and y u and v. And then we have f of uv. Okay, so let's look at the partials of this with respect to u and with respect to v. So with respect to u, we're going to get 1, 0, fu. And with respect to v, we're going to get 0, 1, fv. So RU cross RV, we actually go ahead and find what that thing is. It ends up being minus fu, and then a minus fv, and then for the z, it ends up being 1. So the magnitude of that, I know we don't need it here, but I just want to show you what it looks like. It's just the square root of fu squared plus fv squared plus 1. I just wanted to bring this one up real quick because if you've got a surface that's a function and you're doing just a surface integral, this is your Jacobian. It's super fast. You just take the partials, right? And in fact, if we're going to talk about, say, gradients and whatnot, this is actually the magnitude of the gradient. Because if we put that z in there, remember the z, its derivative is 1. So that would have been the z component of the gradient. So just a little connect the dot. But anyway, so if you're doing just a regular old line integral or surface integral, you're going to want to use this piece. But you notice that the RU cross RV is minus FU minus FV 1. All right, well, this is actually the upward orientation, the positive orientation. Because think about the components of that. This RU cross RV, that's the normal vector, right? We already said that thing's going to be normal. It's a normal vector. We have multiple options. But this is the normal vector that's got +1. So it's the positive orientation or the upward orientation. So just recognize that. So this is the upward orientation. If we wanted downward orientation, so you wanted to be on the other side, what would you have to do to that vector to get downward?
Multiply it through by -1.
Yeah, multiply by -1 or change the sign. So in terms of downward, it would be FU FV -1. And this is the guy for downward. Sometimes you're going to want upward orientation. Sometimes you're going to want downward. But the really nice thing is that they have basically the same form, right? All you got to do is multiply by a -1. All right, so cool-ish. So let's actually do one. Let's actually calculate the flux. Let's take a field. Let's take a surface. We'll parameterize the surface, and we'll go ahead and calculate the flux. All right, so how about we go with this guy? Let's go with we've got a vector field of y comma x comma x plus y. Okay, so this is how our field is going to be determined. And let's look at the flux, or at least we'll set it up for the flux over the sphere, or how about this, the unit sphere. And we'll center it at the origin. Centering at the origin will make it easier for us to convert it into a form. All right, so good. Let's at least get it set up. I don't know that we'll actually do the integral because the integral may be gnarly, but let's at least get it set up. So what we're going to want to do, we're going to need to, one, parameterize the surface. Then once that surface is parameterized, we'll put those parameterizations into the field. So we'll convert that thing into the U's and V's. Then we'll find RU and RV. We'll cross them. And we'll take that and we're going to dot it with our field. All right, so cool. All right, so here we go. Parameterize the unit sphere centered at the origin. What's the best way to make that surface? All right, so Victor's suggesting doing the x equals u and y equals v. We can definitely do that, except for the fact that the unit sphere is not a function. Remember that this is only if our surface is a function.
We could do spherical, but use U's and V's instead of R's and thetas.
Instead of thetas and phis. Absolutely. Yeah, let's use spherical. Victor, to get back to your, using the UV, f of UV, we could actually do that if we broke it into two integrals, right? There'd have to be the upper half of the sphere and then the lower half. And that would work. It's totally going to work. I don't want to do that. I'd rather just do one integral. All right, so here we go. R of UV is going to equal, all right, so for spherical, we need rho, or for the x, it's going to be rho cosine theta sine phi. The rho is 1 because it's a unit sphere. So rho is equal to 1. So we're going to get cosine of u sine of v. So theta is u. And then phi is v, basically. Okay, so then we go to the y. Well, that's sine of theta sine of phi. So sine u sine v. And then for the z, it's cosine of phi. So cosine of v, not cove, cos v. All right, so there's R of UV. So now let's get RU and RV and we'll cross them. So RU is minus sine U sine V, cosine U sine V, 0. And then RV is cosine U cosine V, minus sine U cosine V. Oh, no, I lied. That one's just sine U cosine V. And then the last one, this is the minus sine V. Okay, so there's our RU and our RV. So we can cross those. And then we're going to dot them with F. While we're at it, let's go ahead and get F. I'm going to put that right here. You'll understand why in a second. So F, it's going to look like sine U sine V, cosine U sine V, right? Because it was YX. And then the last one's going to be these two added together. So cosine U sine V plus sine U sine V. So there's our field, there's our RU and our RV, all in terms of U's and V's. And so now we need a double integral of F dotted with RU cross RV. And I'm going to go ahead and put the bounds on this. Since we're doing the entire sphere, the U, if we do du dv, U was our theta, so that's 0 to 2 pi. And then V, that was our phi value, which is going to go from 0 to pi. All right, so we ready? Are we ready to get this dot cross thing? And I bet you're looking at that going, I don't want to, right? Finding the cross product and then dotting it's kind of a thing. But let me remind you about something that hopefully you saw at some point. This is what we call a triple scalar product. Does that phrase ring a bell? If not,
Kinda.
Okay, if not, that's cool. Let me just show you real quick. So triple scalar product. This is when you have U dotted with V cross W. It's used for lots of different things. If these are just nice little vectors, it's actually going to find you the volume of the parallelepiped, the box, that's formed by these three vectors as the three edges, for example. But here's the deal with this. If you do a triple scalar product, it's actually just the determinant of the components of each of these vectors in a matrix. So instead of doing the dot product, trying to cover up that light. Oh, get that glare gone. Yeah, that's failing miserably. Hopefully you can see it through the glare, but it's just like the components. You don't actually have to do the cross product and then the dot product. You can just do it all at once, which is why I wrote it like this, because now I've got my three vectors in order and I can just find the cross product. So I'm going to take those guys and multiply them together. That's going to give me a, so we're integrating 0 to pi, 0 to 2 pi of minus sine cubed v sine u cosine u. That's that one. And then I'm going to get 0, because I got that times 0. Then I've got, this horrible thing. So let's see, that's going to be minus sine squared u sine squared v cosine v times cosine u plus sine u. I'm pretty sure is that third one. Okay, and then I get to go and I get to do my subtraction stuff. Okay, well then I'm going to get a minus those three guys multiplied together, which is going to give me a cosine squared u sine squared v cosine v times cosine u plus sine u. And then I'm going to get a minus sine cubed v. Where was I? Sine cubed v sine u cosine u. And then another minus 0. All right, so I apologize for not having a space for my du dv, but you know it belongs there. And that's the lovely guy that I get to integrate to calculate this flux. All right, so why was this one horrible and nasty?
Because it was trig functions.
Yeah, I agree.
It's the parameterization for sure, right? This one, because of its parameterization, is going to be a little bit rougher. But you can imagine, like, what if this had just been, you know, uv and u squared plus v or something like that? It would have been a lot faster, a lot easier, but the process is always the same. So my recommendation when you do this is once you get your R, once you decide what that parameterization is, go in order F, so change the F, then RU, then RV. Because if you've got it lined up like this, that's the matrix whose determinant is what you're going to be integrating. So it'll just save you a little bit of time because it'll already be ready to go. Okay, so calculating fluxes. I mean, it is what it is, right? You have to do it, just you have to blitz through it. But in terms of what it's telling you, again, remember what Flux is telling you is how much is going over the surface. So if you get 0, that means as much is going out as is coming in, or as much is going to the right as to the left, or however you want to think about it. As much is moving in the positive direction as in the negative direction. If you end up with a positive number, that means there's more flow towards the positive direction. Whatever that happens to be. Right, however you end up deciding it. If you get a negative, it means there's more flow in the negative direction. So that's why we actually need to know orientation of the surface. That's why we have to be able to say which side is which. So that when we get a flux number, it means something to us. Because if I just told you the flux is 5, positive 5, through a surface, you're going to look at me and go, okay, which direction? But if I told you I'm using downward oriented vectors, then which direction is a positive 5 flux?
Probably that direction still.
Yeah. So if I said it was downward, I'm using downward pointing vectors, and we get a positive flux, that means there's more flow downward than up. If we're using downward oriented vectors and I get a negative flux, that means more flow is upward than down. And we actually saw that with the line integrals, right? When we got fluxes that were negative versus positive, we had to have an orientation there as well. And you may remember that we always use the same n, right? The same little n. How do we get the little n with line integral fluxes?
We switched around x and y and made one negative.
Yeah.
So we switched the partials and with the x and y, and we made one negative. Which one did we make negative?
X, I think.
Yeah, it was the x. So by doing it that way, always, again, positive versus negative meant something to us. So we knew which direction the flow was going, right? Otherwise, if we hadn't done that, same issue. Here's a line integral. I get a flux of 5. Okay, I mean, that means that there's flow through that curve, but which direction? But by specifying that we're always using this one, right, then we know exactly which side's positive, which side's negative, and now we know, right? So it's the same kind of idea. You need to know your orientation on your surface for this to even mean anything once you get a number. All right, so there's just a little bit more about surface integrals. Specifically, I wanted to show you a flux integral so you could see how it plays out. Anyway, I'll leave this to you. Have fun sometimes and sometime and integrate that. I'm going to guess it simplifies a bit, probably a lot actually, if we use some trig, specifically sine squared plus cosine squared stuff, but I'm not in the mood to do that right now. Which, for those of you who know me, should tell you my mental state. Oh, it's not good. I don't even want to do trig. Yeah, I'm not in a good place right now. Anyway, all right. So any questions on this guy, other than what the actual answer is?
So do you think that if we had done the two integrals creating functions of r, u, and v, I think that would have been easier to integrate than this?
No. No, because if we had done that, we would have had square roots for our z equals. You would have the square root of 1 minus x squared minus y squared. The partials of those are going to be kind of gnarly. Also, we'd have to do the orientation for one of them. It would have to be, if we did upward orientation, let's say on the top, we'd have to do downward orientation on the bottom, because upward orientation on the top means arrows are pointing out of the sphere. And so to keep it with arrows pointing out of the sphere, we'd have to go downward down below. So we'd have to keep track of that. And I don't think the integral would be any nicer, because think about getting RU cross RV with square roots and all kinds of stuff. You know, I doubt it. The one thing we might have been able to do in that case is a polar kind of deal. Once everything was done, polar might have been a friend that could have helped out. So, you know, I'm not really sure. It's probably going to be equally nasty, but for different reasons, if you know what I mean.
Yeah, makes sense.
Yeah, and by this point in your math career, you really do know what I mean. That a lot of times the shortcuts that we take are not really shortcuts. It's just trading one thing for another. All right. So I'm going to move back to my computer because I want to use the, I want to show you guys the quiz. I want to go over the quiz and stuff like that. And that's a little bit hard to do, sharing screen via my phone and all that. So I'm going to go hop back down over there, but I'll be back with you in just 1 second. All right. So hold tight. All right, so let's talk about this exam that's coming up. Right, so we got an exam on Friday. In terms of what it's going to cover, like I told you last time, it's going to be sections 6.1 through 6.5. At least I'm pretty sure that's what I told you. Let me just confirm with the book here real quick. Because I want it just to be the section that go through the section on divergence and curl, yeah, which is 6.5. So it'll be 6.1 through 6.5. The quiz you guys took, the last quiz you guys took, like I said, I'll have those grades in for you soon. I do want to go over it though, because that covered a couple of these sections. So just so that you are prepared for at least that part. So let me go over the quiz, and then once we're done with that, we'll kind of do the general review of what kind of things you need to know, what to expect on this exam. Okay, so let me share my screen and pull up said quiz. All right, so number 1 was find the potential function of the conservative vector field given by this, for this field. So we know how to do that. In fact, I think we did talk about this. I forget, somebody asked me about it a little bit, so we kind of went through it. But how do you check to see if something's conservative? What do we do?
For this one, it's like 3 things that I don't have memorized, but I have them written down somewhere.
Okay. I appreciate that one there, Seamus. Okay, so Seamus, there's the 3 things that are written down somewhere that you have to check.
A bunch of P's, bunch of Q's, bunch of R's, some X, Y, and Z's.
Exactly, some combination thereof. All right. And in the chat box, Victor just put curl. That's a good way to think about it. Now that we've gotten to that section, you can check and you can determine if a vector, vector field is conservative by looking at the curl. And what has to be true about the curl? Has to equal 0. Good. Okay, so we can always just check the curl and see, is that equal to 0? Now the curl, yeah, it's that 3-dimensional thing that we can calculate. So as Victor says, it's the cross product of the partials. Yeah, think of it as del cross f. That can help you a bit. So basically what you need is you need the partial of, well, here's what I do. The way I think about it is I think of all the 3 different combinations that you can have. You can have P and Q, P and R, and Q and R. And for each one of those, you want to do the partial with respect to the other piece's variable. So like with the P and the Q, you need P sub y and Q sub x. For the P and the R, you need P sub z, R sub x. For the Q and the R, you need Q sub z, R sub y. So you need to see that those things are all equal to each other. And then once you know that it is equal, then you can do your antiderivatives to find these, or to find that potential function. Okay, so I know that this didn't ask us to check to see if it was conservative, but seeing you might need to be able to do that on the exam on Friday is probably worth talking about it. So let's go to a whiteboard and we'll go ahead and work this one out. And I'm actually going to go ahead and start with the showing you that it is conservative. So let me just write down the function here real quick. Okay, so here's our partial check. We're going to take px and, oops, sorry, not px, py and qx, right? So that was the p and the q. So py, well, that's 1. Qx is 1. All right, so those check. So then we're going to need pz and rx. Well, pz is 0. There are no z's in there. Rx also 0. There are none in there. Okay, and then the last one we're going to need qz and ry. So qz, that's just 2y, and ry is also 2y. So all of those guys, all sets of those are equal. So I know that the curl of f is 0. I know that this thing is conservative. All right, so if we're going to find our potential function, all we're going to do is we're going to integrate these things with respect to the various variables. So we're going to do partial integrals. And we're going to see what we get. Okay, so for the first part, we're going to integrate with respect to x. So that's going to give us sine of x plus xy. There can be more stuff. It's just going to have to be not in terms of x. All right, so then we go to the next piece and integrate that with respect to y. Well, the x gives us xy. That's already there. We're going to get an ey, and we're also going to get a zy squared from this piece. All right, now we go and we integrate this last part with respect to z. Y squared gives me zy squared. And then I have to integrate inverse tangent of z. If you were going to do that by parts, or by hand, you'd have to do it by parts. Or if you're lazy like I was, you'll just use a calculator or some other equivalent to integrate inverse tangent. And it's this guy right there. So there's your potential function. And now if we are doing some sort of a line integral or whatever, we could use the fundamental theorem, this, that, and the other thing. All right, so good for number 1. Any questions on that? Okay. So Victor just said, should there be a plus C? That's a very good question. It depends what you're being asked. If you're asked to find a potential function, this is good enough. If you're being asked to find the potential function, well, then you should probably put a plus C on it. If we're actually using it, like with the fundamental theorem, that plus C doesn't matter. So watch the wording. I'll just tell you, when I write on an exam that I'll write find a potential function. So if you want to put plus C, go for it. You want to put plus 28. That's cool too. I don't really care. But I'll just ask for a potential function where this would be enough. But that's a good question. All right, so good for that one. All right, well, then let's go back to the quiz and we'll look at number 2 here. Okay, so number 2 is asking us to do a line integral. And what we've got is just the function x squared y, but we are going over a curve, and this curve is the ellipse that's given by 2 cosine t, 3 sine t. All right, so yeah, what are we going to do here? Well, first of all, I want you to notice that I was kind of nice, and I already gave you the parameterization for your curve. So we don't actually have to do anything with that. So once you have your parameterization, what do you do?
Differentiate
prime.
it.
Okay, so I said the R prime, right? We're going to differentiate it. We're going to basically replace everything in here with that parameter, right? So we're going to change the x squared y. We're going to put in 2 cosine t for x. We're going to put 3 sine t in for y. And then we need to integrate, or we need to change our ds. And how do you change the ds? What does that equal? How do you get it in terms of dt? What do you have to put in as the Jacobian?
Magnitude of r prime dt.
Okay, good. So it's the magnitude of r prime. Okay, so let's do that. So we'll go over to the whiteboard again. Let's just clear this guy real quick. All right, so we're integrating x squared y ds. Now we got r is 2 cosine, 3 sine. All right. So r prime is minus 2 sine, 3 cosine. So the magnitude of r prime is the square root of 4 sine squared plus 9 cosine squared, which, if you guys don't mind, just because it'll be easier, I'm just going to make that 4 plus 5 cosine squared. Take 4 of the cosine squares to go with 4 of the sine squares to turn into 4. Those are the remaining pieces. So this integral then is going to be 4 cosine squared times 3 sine times the square root of 4 plus 5 cosine squared dt. And then what are the bounds on t?
0 to 1.
Okay, not quite, not 0 to 1.
0
Oh,
to 2
0
pi.
to-
It's going to be 0 to 2 pi.
Hey, Bruce, how did
Hey.
you go from 4 sine squared t plus 9 cosine squared to 4 plus 5 cosine squared?
I did this. And then
I'm salty about that. I'm not gonna lie.
I'm salty as
Yeah, no,
well.
I totally agree.
what do you mean?
That is
It
that's
I
looks
didn't
pretty-
even
so
know you could
easy,
do that.
but yeah, I feel stupid for not
I
thinking
feel
about it.
stupid as well.
Okay, well, all right. So first of all, you feeling stupid or whatever, that's on you. Second of all, no. Yeah, this is just one of the many tricks that you learn along the way that can help you a lot when you're dealing with these trig things. Yeah, but if you don't see it, like you can still do the integral, right? I mean, especially if you've got technology, but this really helps if you don't have technology, right? Because check this out. If I've got now 12 sine cosine squared times the square root of 4 plus 5 cosine squared, right? Like I can just type this into my calculator. That's not a big deal. But if I was going to try to do it by hand, this is now where you're going to want to do the, well, let's let u equal 4 plus 5 cosine squared. So du is going to be 10 cosine minus 10 cosine sine. And you've got a cosine and a sine. So that can definitely help you with the substitution. You still have a cosine left over, but you can solve that in terms of u. And then it ends up just being a square root of some stuff we'd use in it, right? But the point is, it's not necessary to be able to see that jump right there. It's just useful. Anyway, so like I said, at this point, it's just a matter of do the integral. And I don't remember what that value is, so I don't really care at this point. Anyway, so is that okay for that one? And don't be too upset about this step. That's just, it's just a thing. All right, so go for that one.
Yeah.
Ish. All right, so
I
there
wish
was
I would
no,
have seen that in the quiz, but
yeah, well, next time you'll see it, right? All right. So yeah, so Matt just said that trick is kind of brilliant. I agree. It's really, really nice. And why do extra stuff if you don't have to, right? Why deal with both sine and cosine if you can just deal with one of them? At least that's my motto. All right, so let's go look at number 3. So number 3, we got a field. So it's in there, the x, 3xy, and x plus z. And then we want to find out how much work is done along the particle moving on a line segment that goes from 124 to 201. All right, or sorry, 20 minus 1. All right, so what are we going to do here?
First, find r
So,
given our
what-
points.
Okay, so again, first parameterize. We've got our points, we can parameterize that line. And so then since this one's a work integral, what do we do? What do we integrate?
We dot it with t.
Not with, yeah.
So it's f dotted with t ds, but if it's parameterized, what's the shortcut? Or not the shortcut, but the usable form?
Our good friend R prime.
Yeah, f dotted with r prime. Okay, so let's go back to the whiteboard. All right, so we're going from, let's do r first. So we're going from 124 to 20 minus 1. All right, so the trick here is to find a vector that connects those and then use our points to add to a scalar multiple of that vector, a t multiple of it. So let me build the components this way. So the 1, 2, and 4, those come from my first point. And then in terms of my vector, I'm going from 1 to 2. So I'm increasing by 1. So I'm going to 1t. From 2 to 0, I'm going down by 2. So I have minus 2t. And from 4 to minus 1, I'm going down 5. So I've got 1 plus t, 2 minus 2t, 4 minus 5t. And the way that I've got this set up is that the t's are going from 0 to 1. So if you do it this way, where you always start with the first point as the numbers there, and then you find your vectors by figuring out the change from the first to the second, your t's are always going to be from 0 to 1. Okay, so that makes our f, whoops, oh yeah, it's got the x, so 1 plus t, then it's 3yx, or 3xy, so 3 times 1 plus t times 2 minus 2t. And then the last one is x plus z, so 1 plus t plus, like that, plus 4 minus 5t. All right, so that's our f. Let me just simplify that really quickly. That's 1 plus t. This one's going to be 6 minus 6t squared. And then that guy's 5 minus 4t. All right, so then we need r prime. Well, r prime is actually just the vector that connects those guys. So now we're going to integrate from 0 to 1 of f dotted with r prime. So that's going to be 1 plus t minus 12 plus 12t squared minus 25 plus 20t. And again, at this point, I don't feel like doing any more. But you integrate that guy and you're done. All right, so any questions on that one? All righty. Okay, so let's go find that last question and take a look at it real quick. All right, so the last one here. Calculate the flux of f equaling xy squared, x comma y squared, over the curve y equals x squared from 0, 0 to 1, 1. Okay, so how are we going to do flux?
F dotted with little n.
Okay, so we're going to do f dotted with little n. All right, so how do we get little n?
Find r prime, and then switch the coordinates and make one of the x negative.
Okay, good. All right, so first things first, we need to parameterize. Again, if you haven't caught that yet, that's pretty much how every line integral ever is ever done, right? You got to parameterize. You got to parameterize your curve, and then you can, go from there. Okay, well, anyway, so we need to parameterize. So our curve is y equals x squared. So that means the parameterization is going to be easiest if we just do, say, x equals t and then y equals t squared. Right, so we can do this as t comma t squared. And again, the t's are going to go from 0 to 1 because we were told we're going from 0, 0 to 1, 1. So that means that our field then is going to be t to the fourth, because it was x comma y squared. All right, so let's get r prime. So r prime is 1 comma 2t. So we're going to swap them to get little n. And we're going to make the x negative. All right, so we're going to integrate from 0 to 1, f dotted with n dt. So it's integral from 0 to 1 of 2t squared minus t to the fourth. And I'll go ahead and do that one for you because it's easy enough. Oh, I totally lied. It's not 4, it's 7. Seven fifteenths. Okay, so that means it's 7/15 pointing in the direction of this n. So let me kind of circle back to what we were talking about just a little bit ago with surfaces and the whole plus or minus. Because this one, if you look at how we've got this oriented, so here's our y equals x squared, and we're here between 0 and 1. If you look at our normal vector always has a y component of -1. So it's always in the downward direction. So these guys n, the n we're using are these guys. Now notice that these are not unit, right? This is not a unit normal vector, but it is normal. The magnitude ended up canceling out with the ds when we go to this form. But the fact that we have 7/15 tells me that this field is such that there's more flow downward through this curve than upward. And in fact, let me pull up Desmos, or no, not Desmos, because I don't know how to graph a field on Desmos. Let's pull up a field mapping thing of some type, and we will let's see what that looks like, so you can see that more of it is going through. I think it's funny that if I type field, the first thing it pulls up for me is Field of Dreams. I don't think I've ever Google searched Field of Dreams. However, it's probably quite appropriate because a lot of what I do look at is baseball. I'm telling you, Google knows a lot about me.
It's frightening.
Yeah, a little bit. But also, I don't know, let them know that about me. I don't
At least
really
you can
care.
sleep well knowing that they know everything about everybody. So,
well, yeah, there's that. But also, what do I care, right? Like, so Google knows that I like to watch baseball and drink high quality root beer. Well, guess what? So do you guys. So does everybody who's going to watch this on YouTube. Shit, my next door neighbors probably know that about me too. So, All right, for some reason, my computer is really not letting me do anything here. Hold on. And clearly my dog can tell I'm in distress. She just walked in. She's like, what's going on? All right. Well, let's try somebody other than GeoGebra if GeoGebra is gonna be a problem, we'll go elsewhere. Let's see what academo.org does. All right, so let's see. We were looking at xy squared, right? So let's just go with x. And this one we're going to go with y squared. Probably because I have to have some sort of a whatever on it. Let's just do ax by squared, update. All right. This actually doesn't really help us much at all unless I can zoom in. Because do you remember where we were looking? We were on the y equal x squared from 0, 0 to 1, 1. All right. I'm officially going to stop sharing because as soon as I start seeing those kind of warnings like page unresponsive, I get nervous. Anyway, if you actually look at the vector field, you'll see that more of it is pointing kind of through y equal x squared, but to the underside of it, which is why we ended up getting a positive 7/15 for that problem. Anyway. All right, so there are the answers to that quiz, and that should be a pretty good review of the line integral stuff, of the various line integral types and things that we did, because there was a work integral, there was a flux integral. We found out if a field was conservative and stuff like that. So other things to know for this exam, right? So if we just kind of go and order these sections, for sure, just know, like 6.1 was about fields. So know about fields, how to graph them, what they look like, what they mean, what it means if they're conservative or not, all that, right? And then 6.2 was about line integrals themselves. And with line integrals, the important things are being able to do them. And we really had the three types of line integrals. There was just the regular old line integral, where we're integrating a function. Then there were the work integrals. So that was a vector line integral where we're dotting f and t. But in the useful form, it was f dotted with r prime, right? So that's a work integral. And then we did flux integrals. And that's f dotted with n, big N. But again, the useful was the little n, which we just did there, where we swap the x and y components of r prime, and the one that was x, we make it negative when we put it into y. But realize that that's kind of arbitrary. That's just choosing a direction. So we know, like in the case like I was talking about with the y equal x squared, I know more of the flow is going downward through the graph of y equals x squared. Okay, so that was 6.2. So then in 6.3, this is when we talked about conservative vector fields. So things to know there, know how to tell if it is conservative. If it is conservative, be able to find its potential function. And then use the fact that with conservative vector fields, we know a lot. We know that when we're doing work integrals, when we're doing work integrals, the path doesn't matter. Going from point A to point B, all that matters is where we started and where we ended. So you can choose your favorite path. If you just want to make a beeline and go straight, go for it. If it's easier to follow coordinate axes, do it. It doesn't really matter. Also, we have the fundamental theorem of line integrals, which says if it's conservative, we can find the potential function and then evaluate that potential function at the endpoints and subtract, right? So conservative vector fields are your friend. I've told you many times that what I do when I'm in a field is the first thing I do is I check if it's conservative, always. Because if it is, then I know going forward it's going to be a lot easier. Okay, so do that check. It's pretty quick, especially for vectors that are just two components, right? Anyway, so look for conservative vector fields. So if it comes down to it, make sure you know the fundamental theorem so that you can use it, and the other stuff we know about conservatives. I don't know if this was in that section, but similar to conservative vector fields are the ones we call source-free fields. And those were the ones that had like the same properties, but for flux integrals, as opposed to the work integrals. So if you have a flux-free field, then the flux on a curve is independent of what that curve looks like, just where it starts and where it ends. Instead of a potential function, we have what's called a stream function, right? But it plays pretty much the same role. I'll talk a little bit more about flux free fields later, but that's another thing to kind of recognize. Okay, so after we talked about conservative vector fields, then we went to Green's theorem. So remember what you need to do Green's theorem. What do you need? Like, what are the requirements for Green's theorem?
The field is not conservative.
That actually isn't necessary.
Yeah.
Green's theorem still works if the field is conservative. It's just we never use Green's theorem.
You need a line integral with a dx and a dy in it.
Okay, so we need to have, and I see here Victor said we need a simply connected region. You need a curve, a closed curve around a simply connected region, right? And so that's your line integral, kind of like, who was it? Jacob was just saying, right? That you got to have this line integral on this closed path. And it just has to be a simple closed curve, but we need the right orientation. This is a place where orientation mattered. Do you remember what it had to be?
Counterclockwise.
Yeah, it had to be oriented counterclockwise. But as long as you've got that, you can turn it into a double integral. And it's a double integral of qx minus py. So it has to be a two-dimensional thing, right? We'll see later how you do three-dimensional-ish things like this. There's a 3D equivalent with surface integrals, but regardless, basically it just turns it from a line integral into a double integral. If you have a conservative vector field, the qx minus py ends up being 0. And so we went over a closed path. Well, we know that the total work in a conservative field over a closed path is 0. Well, that kind of comes from that. So Green's theorem, where that's really useful, is finding the work done on a closed path when it's not conservative. And so sometimes you can make life easier. Instead of trying to do it as a line integral with the parameterization and whatnot, you can turn it into a double integral and it can be quick. Like we saw that example of where when we did it, we got the qx minus py was a constant. And so we're able to just take that constant times the area of the region. There was a homework question I think maybe Seamus asked about a couple days ago. That was that circle that was centered somewhere weird. And the parameterization would have been horrible. But the double integral, it ended up, we're integrating 6 or something. So it was like, oh, so it's 6 pi r squared. So Victor just put in the chat, how can you be sure about the direction? That should be given, right? Like it should be pretty clear from the context of the problem. You know, like, okay, so basically it'll say something like, find this integral where C is the curve given by whatever. So it'll be something like where the curve is an ellipse being traversed counterclockwise, or it's the triangular region going from 0, 0 to 1, 1 to 1, 0 back to 0, 0 or something like that. And so it should be pretty clear what direction you're traveling, because otherwise it's an incomplete question, right? Like if I asked you, what's the work done to go from point A to point B, and it's not conservative, for example, you need to know, right? What is that path? How did we go? So without that, it's not actually a complete question.
Is it generally given by the function value of the field or the vector value of the field?
It won't be given by the field at all. The direction has nothing to do with the field. It has everything to do with the curve. So in the description of what C looks like, that's how you're going to get what the orientation is. And then, so Victor, yes, you are correct that if you end up going clockwise, you just change the sign. Okay, so Green's theorem, again, when can you use it? Well, it's got to be a closed path. And we use it when we're doing a vector line integral. So you can use it for work, but there was also the form for flux integrals. And with flux integrals, it looked a little bit different. Now it was the integral of px plus qy. And that came from the whole swap, change the sign, blah, blah, blah. But you can also, there's a Green's theorem form for flux as well. So really you want to look at Green's theorem when you're doing any kind of a vector line integral over a closed path. So remember that one on the quiz where it was do the line integral over an ellipse? That one, you might be tempted to go to try to do Green's theorem because you go, okay, cool, I'm over a closed path. But that one wasn't a vector line integral, right? There was no field involved. It was just a plain old function. So what I do when I'm kind of looking at these things is I look, if it's a closed path, that immediately gets me, whoa, Green's theorem? Like that pops up, like if it's like I got a bunch of little prairie dogs in my head and all of a sudden Green's theorem and the prairie dog like pops up like, wait, did I hear Green's theorem? Green's theorem, right? So that little guy gets triggered. But then I have to be like, no, get back down into your hole. This isn't a vector line integral. We just got to do it regular old line integral way, right? But if it's a vector, so either a work or a flux, then yeah, totally, I go to Green's theorem. All right, so Green's theorem, and then the last section on the test is flux and divergence. So be able to calculate flux, be able to calculate divergence. They're pretty easy, divergence especially. What they tell you, remember, divergence is sort of a measure of flow. And did I say divergence and flux? I meant divergence and curl, sorry. And then curl is a measure of rotation, how much rotation actually happens. So both of them are built from partials. And if you think of that del operator, think of the divergence as del dotted with your field, and curl is del crossed with your field. It can help you get those quantities. Divergence is a scalar. Curl is a vector. But those we actually use for checks on conservative and source free. So conservative vector fields, we kind of already hit that, the curl is equal to 0. If the divergence is equal to 0, then it's a source free field. And then you know all of the kind of equivalent things to conservative vector fields and work integrals apply. So anyway, so that's what this exam is going to look like. It's going to be pretty much the same as always. We'll start it at the usual time. I know a couple of you have different times, and I forget who it was. Somebody sent me an email recently about adjusting the time a little bit. The answer to that is going to be yes. Let me just get to it. But it will start like normal. We don't have class, but I will be in here if you have questions. So feel free to pop in. And I actually have another Zoom meeting going on at the same time. So if it takes me a second, like if you see me kind of talking somewhere else, I'll get to you in just a second. All right. But I will be around. I also have office hours tomorrow, my usual time from 10 to 12. So if anything pops up, you can come find me. Anyway, so I think that's pretty much it. By this point, you kind of know what to expect. It's just going to be line integrals, line integrals, line integrals, line integrals, right? Just lots of different forms depending upon what I'm trying to get at. So
you have office hours tomorrow, right, Bruce?
Yep, 10 to 12.
Okay, cool.
All right. Okay, well, then with that, I'm going to stop the recording.